Happy day, everyone. So this lesson today is on thermochemistry, and we're starting this new unit on thermochem. And so we know that when we say the word thermochemistry, we're talking something about heat and energy, and that's exactly what we're talking about here. So we can see here that we know that this is an issue on Earth right now, today. It's very important. We're looking for better alternatives to fueling aspects of our lives. And so what we're going to be discussing is basic concepts dealing with energy like work, enthalpy, Hess's law, calorimetry. How does it work? How do we measure this energy? And we hear a lot about it, but do we really know how it's being measured? Let's start off with a very simple reaction. It is the reaction between hydrogen and oxygen in order to make water. Now, there is a big boom that goes off when you actually make the water, and it requires a little bit of energy just to set it off. And once you do and you get it over the activation energy barrier, then there's a lot of energy that ends up being released. And so if we can harness that and use that energy, then that would be brilliant. But the problem is that we've had some explosions happen. So let's just start off by watching what had happened. If you've ever heard of the Hindenburg, the German airship back in 1937 that ended up exploding, let's just take a look to watch what ended up happening here.
1937. The Hindenburg, the world's largest flying machine, arrives in the United States with 97 people on board. It's the end of a successful transatlantic flight. Moments from landing, a fierce fire erupts. In just 34 seconds, the mighty airship is destroyed. 36 people perish. Many suffer agonizing burns. But what caused the devastating fire? Now, a 21st century air crash detective re-examines one of the most famous air disasters in history. Using advanced computer simulations, we reveal what really destroyed the Hindenburg. Disasters don't just happen. They're a chain of critical events. Unravel the clues and count down those final seconds from disaster. 14 minutes before the fire, the Hindenburg begins its final approach. Static electricity builds up on the ship, spread evenly throughout the structure. 11 minutes to go. Without warning, the wind changes direction. Instead of going around the airfield in a wide sweep, Captain Bruce, anxious to land the airship as soon as possible, makes a sharp left turn. Stressed by this sudden maneuver, somewhere near gas cell 4, a bracing wire snaps. The gas cell ruptures and hydrogen begins to leak out.
Okay, so you're hearing this, the hydrogen starts leaking out.
8 minutes before the catastrophe, Captain Bruce notices that the ship is tail-heavy. He orders the crew to dump water to balance the ship. Then Bruce orders another sharp turn, this time to the right, to line up with the mooring mast. The ship is still tail-heavy. Captain Bruce orders 6 crew members to walk to the nose to try to counterbalance the sloping tail. But Bruce is too concerned with landing to realize that the airship may be leaning as a result of hydrogen leaking. 4 minutes left. The Hindenburg comes to a stop, and the crew drop the mooring ropes. Eyewitnesses on the ground notice a fluttering effect near the tail fin. They don't know it, but what they're seeing is leaking hydrogen pouring out of the doomed machine. By 6:25 p.m., due to falling rain, the ropes are now wet. The electrical charge flows from the metal part of the airship to the ground. The aircraft's skin, less conductive than the metal, is still highly charged from a combination of the journey and the atmospheric conditions. It's now at a dangerously high voltage. Seeking the quickest way to the ground, a spark jumps from the outer skin to the metal, igniting the leaking hydrogen. The fire roars through the airship as 200,000 cubic meters of hydrogen in the 16 cells catch fire. 34 seconds later, the mighty Hindenburg is destroyed. 36 people are killed.
So obviously a brilliant idea, but then a terrible disaster that came from it. And something similar as far as the Challenger space shuttle in 1986. So what we're going to start with is, what is this thermodynamics that we're talking about? And there's the first law of thermodynamics. There are actually 3 laws of thermodynamics, but we're only talking about the first law here in this unit. It states that the energy of the universe is constant. It's that simple. The energy of the universe is constant. Energy in is energy out, and nothing is actually lost. This is also known as the law of conservation of energy. Thermochemistry is concerned with heat changes that occur during chemical reactions, and there are 2 ways to really transfer energy. So one is in the form of heat. So we are saying, like, if you take a piece of ice and you melt a piece of ice in your hand, and then energy actually needs to be absorbed by the molecules, and so they steal your energy in order for the melting to happen. The other type is apparent when you buy gasoline. You're purchasing the stored potential energy that it contains, and this energy can actually be used to do work to propel the car. Okay, so now we're talking about delta H and heat transfer. Let's talk a little bit about exothermic and endothermic reactions as well. So delta H, when we see this delta H, it's simply the heat change, which is what we call enthalpy. So we're going to list some delta H values here. And there are many delta. You can have a delta H for almost anything, okay? So you can have a delta H of combustion, so COMB. You can have a delta H of vape, which is vaporizing something, so the conversion from liquid to gas. You can have a delta HF, and this is not the cursive F. This is for fusion, okay? And fusion is actually defined as whether a substance is either turning into the solid phase or into the liquid phase. So either going from solid to liquid or liquid back to solid as melting or freezing, okay? And so the way they define it, though, is they actually say that it is a substance melting is what they define the heat of fusion as. So there are a whole bunch of different ones. But a very common delta H, just very basic delta H, is simply delta H RXN. And RXN is for any reaction, okay? So you can really put a subscript of anything there. One of the most important ones that we're going to be working with in this unit is delta HF. And so it's given this symbol delta H with this little zero that just basically refers to it being standard. And then we put this cursive-y looking F down on the bottom, okay? And this is called the heat of formation. And so we talked a little bit about this heat of formation. And if we end up looking at a thermochemical chart, those are heats of formation that are being given to us. If you've ever had to calculate where you're trying to find the net energy change for a particular reaction, you use the heats of formation for every single substance, and then you use products minus reactants, which I'm going to show you here. We need to make sure that we have this definition down, okay? So what is this heat of formation? It is simply the energy, and it can either be a positive or a negative value, and positive simply means it's absorbing energy, and negative means it's releasing. So it's either the energy absorbed or released for, well, what are we doing? We are forming a mole of the substance. For the formation of 1 mole, so we have to be specific, of 1 mole of a substance from what? Well, the way that they form these substances is from their elements. So we're actually making them from their elements in their natural states or in their standard states. From their elements in their standard states. Okay, and so we're going to end up remembering this. So we'll kind of go over this a few times in this unit. So there are different units of energy that we can use. And so one of the units that we end up using that's very common in chemistry is the kilojoule. Okay, so the joule or the kilojoule. So you might be familiar with the food calorie. Capital C calorie is actually equal to 1,000 calories. So when you see the food calories, that's a capital C. And so really, it's 1,000 calories, which is simply 1 kilocalorie, okay? So 1,000 calories is equal to 1 kcal. Now, what is a calorie? Well, it's 4.184 joules. And so we want to make sure that we have this down. It requires 1 calorie of energy to raise, and I'm not sure if any of you remember this, but to raise the temperature of the amount of 1 gram by 1 degree Celsius. So it requires 1 calorie of energy to raise 1 gram specifically of water. So we're going to talk about how these definitions can be different. If it's any substance, what do we call it? If it's water, we call it the calorie by 1 degree Celsius. So here's what I have. I actually have a gram of water. It's a milliliter of water, but since the density of water is about 1 gram per milliliter, then this right here amount of water, I would take a thermometer, and as soon as I start heating it up and it goes up by 1 degree Celsius, then that is what a calorie is, okay? That amount of energy is what a calorie is. And so that's how it's defined, or 4.184 joules. So, and this is switching, if you wanted to switch to from joules, kilogram, it's the same thing as a kilogram times meter squared per second squared. So later on, when we end up doing calculations, it'll make more sense as to how these units are actually working out. Okay. Exothermic reactions. So what we had looked at in class, we had a demonstration on hand warmers. And so the question is, how do these hand warmers work?
To understand the chemistry here, let's first take a look at the ingredients. Inside every hot hands hand warmer, there is iron powder, water, salt, carbon in the form of activated charcoal, and vermaculite. On the outside of the package is oxygen in air. Iron meets with oxygen from the outside along with salt as a catalyst and produces iron oxide, Fe2O3. This is an exothermic chemical reaction.
And that's the kind of the big part of all of this, is that exothermic reaction that ends up happening right there. But how do they keep it going?
Meaning that heat energy is released in the making of the ionic bond. The vermaculite helps keep the heat contained and hot within the reaction. And just like the coals on a barbecue, the charcoal helps dissipate the heat to the entire hand warmer. As long as iron keeps reacting and the carbon stays warm, the hand warmer will stay hot. After a while, the reaction stops and the carbon cools down, making the hand warmer irreversibly return to its initial state. So the next time you hit the slopes or use hand warmers for anything, you can thank iron oxide, charcoal, and chemistry for keeping you toasty warm.
Okay, but the reaction that we actually did was we took calcium chloride and dissolved it in water. That was it. It was a very basic reaction, so easy, dissolving, more of even a chemical process versus a chemical reaction if you're talking about just dissolving something. And what we noticed was it felt hot. So we know that to touch, it actually felt warm or it felt hot. And when I looked at it, the temperature went from around 22 degrees Celsius and it rose up to around 50 degrees Celsius on the thermometer. So what happened? Well, we know that energy must have been released. And so we would call this an exothermic reaction. Now our sign. The sign for delta H then ends up being negative. If energy is lost, we say that it's a negative sign. And so heat, if anything is lost, if you remember, we go in on our reactants and out on the products. So then that means that heat must actually be one of the products. It must be on the product side. And so we can see here that we've got heat there, okay? I had actually looked up what the energy change was, and it actually ends up being that the heat change is 81.3 kilojoules for every 1 mole of calcium chloride that dissolves. Now, the way that we would actually write this, if we wanted to write it outside of the equation, is we would rewrite the entire equation, but instead we would simply say the delta H, and usually what they do is they write of solution, because instead of it being solid, now it's in a solution, is equal to a negative 81.3 kilojoules. Okay, so that's a different way to write it. As far as an endothermic reaction is concerned, well, everything is pretty much the opposite here. So our delta H must be positive in sign. Energy is actually absorbed or gained. When we felt the bad, we actually took ammonium chloride or ammonium nitrate. In our case, it was ammonium nitrate. And we dissolved that in water. And so when we did that, it actually felt cold. And the temperature, I believe, went from about 22 degrees Celsius down to around 8 degrees Celsius. So it was a temperature drop. And heat ends up being a reactant because we are gaining energy in this case. So you can see heat on the reactant side. Again, what we can do instead is we can say the heat, the delta H, for creating the solution of this is actually equal to a positive, and typically in thermo we do include the sign. Now I looked this value up, and this happened to be a 25.7 kilojoule per mole value. And again, that's kilojoule for every 1 mole of the ammonium nitrate that actually dissolves. Okay, so next we're going to be talking about calculating enthalpy change theoretically, because we can do it experimentally. That means that we're in the lab and we're using something called the calorimeter. But if we're doing it theoretically, we're using charts and we're doing these on paper. Enthalpy can be calculated really easily using those delta HF values. And it's a very simple calculation. All we have to do is take the sum of the products, subtract the sum of the reactants, and that's going to give us our delta H. Okay, now, how does it ever get challenging? Well, you have to include the moles as well, so you need to make sure that you're including those. And the other thing that you need to make sure of is that you're doing your algebra correctly, okay? Sometimes you're not being asked for the total, and so you want to be careful with that too, because that could take a little bit more of, I guess, math, just algebra. It's pretty easy though. So sometimes you might actually be looking for one of the products, or sometimes you might be looking for the delta H of one of the reactants. And so you can use the net in order to figure that out as well. Pretty easy calculation. So we had done the elephant toothpaste demo, and so we used sodium iodide as a catalyst. And what we had noticed was when we put the sodium iodide in with the hydrogen peroxide and the detergent, the bubbles started to rise. And so there were bubbles, and it was the entire solution that basically started overflowing. So it was an overflowing of the bubble solution, of this bubbly solution. Okay, and so the detergent was just to create the bubbles. And then what we saw was when we took the splint and we put it in there, that it actually relit the splint. And so we had a positive test for oxygen, a positive test for oxygen gas, for O2 gas, where it relit it. What type of thermochemical reaction is it? Well, there was steam coming off of the top. And so we say that this was an exothermic reaction. So what's the sign? Well, if it's releasing heat, then the sign should actually be negative. So write the balanced equation and calculate the value of delta HD for decomposition here. So we've got H2O2, and actually this is aqueous, and it is going to decompose and form water in the gaseous state as steam and oxygen gas. Let's balance our equation. So I know I need two H2s, which means I need two H2s there, and that balances my two O's and my two O's on the other side. Okay, I ended up looking up what the delta H was for this particular reaction, and it ended up being negative 196 kilojoules. Okay, so I just want to make sure that you understand this, because sometimes you'll end up seeing that it's kilojoules per mole. Well, this doesn't work out because it's for this reaction as written, and it's not really per mole. It's per mole of oxygen, but it's really for 2 moles of H2O2. So it's important that we end up seeing that. So let's try the algebra out to try to figure out, if I look up on the thermo chart, I will actually see that water's value, water as a gas, is negative 241.82. Now I see that H2O2 liquid is negative 187.8, but they're not giving me the value for aqueous. I also know that oxygen's value is a 0. It's in its standard state, so O2 gas must be a 0. So let's go back to this. Let's enter that negative 241.82 for our water. So this is actually 2 times negative 241.82. So don't forget that we need to multiply by the coefficient. This happens to be a 0. I'm going to call this 2x. 2 times x. I'm going to say that I don't know the H2O2, but I know what my overall reaction is, and it's negative 196. Okay, so using this whole idea here that delta H is equal to my products minus reactants, I'm going to end up solving for it this way. I think it's a lot easier than doing the sum of using the parentheses. Then I can ignore using all of that. Okay, so what I'm going to do here is I'm going to say that I have negative 196 kilojoules is actually equal, so that's my total kilojoules, is equal to my products minus reactants. Well, I can see that my products are 2 times the negative 241.82 plus 0 minus 2x, because I have to subtract the reactant. So I'm going to subtract the 2x out. Okay. Well, to do the algebra, I think it might be easier if I just add the 2x to the other side and add the 196. So I'm going to say plus 2x here, but then I'm going to add 196 to both sides. Remember, what you do to one side, you do to the other side. So now I'm getting that 2x is equal to my 2 times negative 241.82, but plus 196. And so then all I'm going to do is I'm going to take this answer and divide it by 2 to figure out what x is equal to. And I end up calculating that x is equal to a negative 143.8. And as far as sig figs are concerned, so really, because I have the negative 196 in the ones place, I can't really go any further than that. So I'm going to say it's negative 144. Is because your subtraction, adding and subtracting is a little bit different. And so I'm going to say negative 144 kilojoules is what my x would be equal to. Okay, so I just wanted to make sure that you could see how we would solve for that. Okay, so we know that it's important to be familiar with the thermo table, and the units of heats of formation are simply kilojoules for every 1 mole. Not gram, it's always for mole. So let's redefine what delta HF is. It is simply the kilojoule per mole, or the amount of energy per mole, to form the substance from its elements in their standard states when they are at 25 degrees Celsius. So if we end up looking at the chart, then it's very clear on the very first page that it says that it's at 298.15 Kelvin, which is actually 25 degrees Celsius. Okay? All right, and so now we're on question 2. So it says, write the equation for the formation of CF4 from carbon and fluorine gas. Really important that you read this correctly. It's not saying the decomposition, it's saying the formation of CF4. Okay, so I know that it takes carbon in order to form that, but I want it from its elements. So I need to make sure that I check on the thermo chart that it's carbon in its natural state where it has a value of 0 kilojoules per mole. So in order to make this, I know it's going to be carbon in the solid state. And then I am going to add fluorine gas. Well, I know that fluorine gas is in its natural state as F2, it's diatomic. And so then what I'm going to do is make this CF4. Well, then I'm going to need to balance it. So I just need a 2 in front of the F2, and now I am making CF4. Okay, so let's take a look at the thermo chart and get our values here. So what I'm seeing here is, here's my CF4 right here, and so I've got a negative 679.9. I can see that I actually want carbon in the graphite form because I want it as an element in its natural state. And I already know that fluorine as a gas, if we look over on this side, is 0 in its natural state. So really the only number I need is this negative 679.9 because that's how many kilojoules it is in order to form this. So my delta H for this is negative 679.9 kilojoules. Okay, now that's not the question though. The question is saying, how much energy would be released if 25 grams of F2 are consumed? Okay, so it looks like we're going to need a little bit of stoichiometry here. Totally fine, okay? So I'm going to start, I know that I'm looking for energy. So if I'm looking for energy, then I'm looking for kilojoules. I see kilojoules in my problem here, so let's look for kilojoules. So let's start this off. I've got my 25.0 grams of F2. I know that from grams, I can go right to moles. And fluorine's molar mass is 18.99. We're just going to use a 19.0, but times 2, which gives us 38.00. So I've got a 38.00 gram per mole of my F2. And so now I'm in moles of F2. Now, there are 2 things that I can do. I can switch it to CF4. That's fine, but I know that as the reaction is written, so this delta H is for the full reaction. Now, yes, I am forming CF4, that's true, but because it's negative 679.9 minus 0 minus 2 times 0 for my F2, those are zeros, then that's also for the reaction. So what I could do is I can simply say that for 2 moles of F2, it actually will release negative 6, and the negative is its absolute value anyway because we're actually asking for, they're telling us that the energy is released. So it's a negative 679.9 kilojoule for every 2 mole. Or what you can do is you can switch your 2 moles of F2 to 1 mole of CF4 and then say for every 1 mole of CF4 it's negative 679.9. But it's the same thing, you're using a ratio. So let's get this calculation and see what the answer is. Okay, and the answer is 224 kilojoules. Okay, now, yes, negative, but again, because they said how much energy is released, they're basically just looking for the net amount or the absolute value amount of energy that's being released. Okay, let's try another one. It says if the reaction of combining hydrogen gas with iodine absorbs 350 kilojoules of energy, how many grams of hydrogen were consumed? Let's write the equation below. So we have the hydrogen gas, which is the H2 gas. We know that iodine is actually in the solid state in its natural state. And so these are going to combine, and we are going to make H with a +1 and I with a -1. So we're going to end up making HI. Okay, so very important that we know our diatomic. So let's balance the equation again. Well, all I need is just a 2 right in front of there. We're going to do the same thing that we did before now. So in this case, I'm going to take a look at my thermo chart and check to see, well, I already know that the H2 and the I2 are zeros. So I really just need to take a look to figure out what my HI value is. So let's take a look on here. And here it is right here. It's saying that it's a value of 25.94. So let's come right back to our notes. And we know that it's 25.94, but, this is the tricky part. Okay. So I see that it's actually 2 of them. So that's 2 times 25.94. So if we do 25.94 times 2, we actually get 51.88. So the delta H for this is 25.94, but it's 2 times that. And then again, since these are zeros, then I can simply just ignore those. And so say 2 times 25.94, and my delta H for this reaction is actually 51.88 kilojoules, a positive 51.88. Okay, so here we go. We're going to do the same thing that we did. We are looking for grams specifically of H2. We're looking for the grams of H2. Okay, so I'm going to start with this 350 kilojoules of energy. Now, the kilojoules of energy goes with anything. It's not like energy is really assigned to something. So that's how much energy it was when this reaction proceeded. So now I have kilojoules down on the bottom. Well, what in my problem has kilojoules? Well, I know that this 51.88 is representing kilojoules, but I need to be specific. What I can do is I can say 51.88 kilojoules for 2 moles of HI, but why would I do that if I could simply say it's 51.88 kilojoules for 1 mole of H2, because that's what the reaction is representing. So that's for 1 mole of H2. And so now it saves me a little bit of time. I don't actually need to even do real stoichiometry in that situation. I'm almost there now, because now that I know that I'm in moles of H2, well, I'm trying to get to grams of H2. So all I need to do is use my molar mass, which is 2.016 grams for every mole. And when I multiply and divide this out, I end up getting 13.6 grams of hydrogen. Okay, and so that's just a start to thermochemistry here, to making sure that you have a good idea of how these products minus reactants work with a twist, as well as being able to solve, if you're given an energy amount, being able to solve how many grams, or maybe if you're given the grams, being able to solve how much energy can be released. And then we'll go into experimental ways of solving this as well very soon here. So this is more theoretical. Happy day, everyone. Hope you enjoyed this lesson.